Rotational mechanics introduces angular acceleration, torques, and moments of inertia. These ideas are important in analysing things that rotate, but also in analysing things that are not supposed to rotate, and that's a subject called statics. Here we look at angular acceleration and rotational kinematics. This particle travels around a circle of radius r with displacement s along the circumference. From the definition of angle, theta equals s over r. Its angular velocity omega tells us how rapidly theta increases. In other words, omega equals d theta dt equals 1 on r times ds dt, which is the speed v over r. Its angular acceleration alpha tells us how rapidly omega increases. Substituting for omega, we have alpha equals a over r. So, to describe motion with constant or zero angular acceleration, we can simply recall the equations of linear kinematics and divide each term by r to obtain the analogous equations of rotational kinematics. These strong analogies continue into mechanics, but with some interesting complications. In linear mechanics, force produces acceleration, and it's mass that resists acceleration. F equals ma. In rotational mechanics, torque produces angular acceleration, and the moment of inertia resists angular acceleration. Tau equals I alpha. So what is torque? If I apply a force to this wheel, the angular acceleration I produce depends on the magnitude of the force, but it also depends on the displacement r of the point of application of the force from the axis of rotation. It also depends on the angle between r and f. The angular acceleration depends on the tangential component of the applied force, which is f sine theta. So, the magnitude of the torque is defined as Rf sine theta. Sine theta is a maximum at theta equals pi on 2, but it is 0 at theta equals 0, in which case tau equals Rf sine theta equals Rf sine 0, which is 0. Well, this will be familiar to you if you've ever applied your own torque on a spanner to undo a difficult nut. You apply the force at large R, you apply a large force, and you apply that force at theta equals pi on 2 radians, or 90 degrees. You can think of the expression for torque tau as r times the tangential component of f, tau equals r f sine theta, or as f times the minimum distance of the line of f from the axis. In other words, tau equals f times r sine theta. Now, tau is a vector. Torques in different directions cause rotations about different axes. The direction of tau is, by definition, at right angles to r and to f in the right-handed sense. If your right thumb is in the r direction and your right index finger in the f direction, then tau is in the direction of your middle finger. Magnitude and direction of tau are conveniently summarized using the vector product. Tau equals r cross f. In other words, tau equals r f sine theta, and tau is at right angles to r and f in the right-handed sense. For most of this module, however, we consider rotation only about one axis, so we'll consider the torque about that axis and write equations for its magnitude. Newton's first law for rotation is simple. Zero torque gives zero angular acceleration. If we add the first law for linear motion, we can now analyse the forces in structures that don't move, a subject called statics. We saw that moment of inertia I is analogous to mass. Mass resists linear acceleration, and moment of inertia resists angular acceleration. Newton's law for linear motion is total external force equals mass times the acceleration of the centre of mass. for rotation, Newton's laws become total external torque equals moment of inertia times angular acceleration. As we saw, I depends on the mass. All else equal, massive objects require more torque to get them spinning. However, I also depends on the distribution of mass, specifically how far the mass is from the axis. I also depends on which axis. You should try this with a pole or a pencil and feel it with your own hands. It's easy for me to give this pole accelerations of about 1,000 radians per second squared about its long axis. However, about a central perpendicular axis, even with my hands further apart and so a larger torque, I can achieve only about 100 radians per second squared. It's obvious why. About the long axis, no particle is further than a dozen millimeters from the axis. About the central transverse axis, however, the distances are much greater, and they're greater still about a transverse axis at the end. You might like to calculate I for these three cases as an exercise in integration.